Demonstrate charging by friction and discharging from pointed objects with a friend who stands at a far end of carpeted room wearing your leather shoes. Scuff your way across the rug until your noses are close together. This can be a delightfully tingling experience depending on the dryness of the air and how pointed your noses are. So I don't have carpeted, so we're going to use this rug and we're just going to use our fingers because my cameraman's kind of a dude.
Yeah.
So I'm going to act like we're walking across the room in a rug, and then let's see if we feel any tingle with our fingers. I mean, there's a little
bit.
It's a little bit of a tingle, but it's not like a shock. I was expecting more of like a shock. It's like right there, kind of, yeah.
Yeah, just a little tingle.
The next one, gonna briskly rub a comb through your hair on a woolen garment and bring it near a small, smooth stream of running water. Is the stream of water charged is the question. So, go through my hair a little bit. With the comb. This is static electricity on the comb. And then we're gonna use a sink for a small stream of water. And it's supposed to actually pull it or push it. And if you look at the bottom of the stream, you can kind of see it wiggling. That's pretty cool.
Oh, wow.
Yeah, it kind of wiggles the water back and forth. And this is because the water is a neutral with positive and negative charges. When bringing the comb near the water, it attracts to the positive force of the water, and the attraction pulls the water towards the comb. In this cell construction, we got a lemon. This is the paper clip, so stick a paper clip and a piece of copper wire into a lemon and hold the ends close to each other but not touching. And place the two ends of the wires to your tongue. The slight tingle you feel in the metallic taste experience results from a small circuit of electricity pushed by the citrus cell through the wires when you moist the tongue close to the circuit. So get them closed. You can kind of like taste like a metal, like penny kind of taste. It's not too bad. It's not really, I can't really like taste the tingling, but I can definitely taste the metal. Oh, there's a tingle. I think it's a matter of how close you get the two pieces of metal together. Text someone and reveal that you have come to an understanding that has been a mystery for centuries, the nature of light. Explain how light is related to electricity and magnetism. Well, like all lights, light can travel through a vacuum. The transverse nature of light can be demonstrated through polarization. Light does not carry charges, so it does not attract or repel charged particles. Instead, light is an oscillating electric and magnetic field. The light causes electrons in the TV aerial to oscillate, and this oscillation generates an oscillating electric current. I can't do this one because I couldn't find a iron bar at Walmart or any of the places that I went to. But you can take an iron bar and it can be magnetized easily by aligning it with the magnetic field lines of the Earth and striking it a few times with a hammer. This works best if the bar is tilted downward to match the dip of the Earth's magnetic field. The hammering jostiles the domains so that they can better align with Earth's field. The bar can be demagnetized by striking it when it is in east-west direction. So it depends on the magnetic field and the way that the bar aligns. So if it's north-south, that's how you get the charge on there. And then if it's east-west, then that's how you decharge it. The magnetic field would have to be weakened. That's the next one. Earth's magnetic field induces some degree of magnetism. It is most of the iron objects around us. With a compass, you can see that cans of food on your pantry shelf have north and south poles. When you pass the compass from their bottoms to the tops, you can easily identify their poles. Mark the poles either north or south, then turn the cans upside down and note the number of days that it takes for the poles to reverse themselves. Explain why the poles reverse. So we have Chef Boyardee's beef ravioli and our compass right here.
Ravioli.
North is that way, south is that way. And when you pass the compass over, north is now faced south. And then if you go under, north is faced, what is that? West. So north would be up here, south would be down here. So north would be on the top and south would be on the bottom. I didn't have enough time or the amount of days to see how, if this was turned over, if the roles would flip. So I don't know what time period it would take for that to happen. But the magnetic field would have to be weakened for the poles to reverse. For that to happen, the magnetic field would have to be reversed or weakened. Drop a small bar magnet through a vertical plastic tube, noting its speed or fall. Then do the same thing with a copper pipe. Why the difference? So I couldn't find any copper pipe or a bar magnet. The bar magnets are basically the magnets that are shaped like the bar, and then it has the blue and the red, and then it's cut down the middle. I couldn't find any of those or copper tubing. But the reason that it falls slower in the copper tubing is as the magnet falls, it induces a current in the copper pipe. The current creates a magnetic field which opposes the changing field of the following magnet. So the magnet is repelled as it falls more closely. Which is your dominant eye? Test with your far hand. Hold up a finger at arm's length. With both eyes open, look past it at a distant object. Now close your right eye. If your finger jumps to the right, then your right eye is dominant. So hold up a finger, look behind it, and then close your right eye. It kind of jumps to the right, and if you do your left, it doesn't really move all that much. So I guess my right eye would actually be dominant for myself. Stare at a piece of colored paper. We have a couple of different colors. To test which stare at colored papers for 45 seconds or so. Then look at a plain white surface. Instead of seeing white, you'll see the complementary color of the colored paper. That's because the cones in your retina that are receptive to color of the paper becomes fatigued and sends a weaker signal to the brain. Only when all three types of cone cells send equally strong signals to the brain. What do you see on the white surface? So I'm going to use blue, and I'm just going to count out 45 seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45. Oh wow. It's kind of like a pinkish tone. That's actually pretty cool. So basically just like your retina is fatigued and it sends a different signal than what you would normally send to your brain to see a different color. But I just use this index card as the white surface. Simulate your own sunset. Add a few drops of milk into a glass of water and look at a light bulb through the glass. The bulb appears to be red or pale orange while light scattered to the side appears blue. Okay. Well, I tried this with a few drops, and I can barely see the light bulb through it, but it actually does have like an orange tint to it, not so much red, but an orange tint. And I can kind of see how you could get the blue around the sides just because of the milkiness of the water, like the cloudiness of it. You can kind of see blue, but it's not very visible. Kind of have to focus on it really hard. It's an interesting one right there. Set up 2 pocket mirrors. I just found this one at the Dollar Tree. This is the only one I could find. But set it up at a 45 or 90 degree angle, at right angles, and place a coin between them. You'll see 4 coins. Change the angle of the mirror is see how many images of the coin you can see. With mirrors at right angles, look at your face, then wink. What do you see? Now see yourself as others see you. Hold a printed page up to double mirrors and compare its appearance with a reflection of the page in a single mirror. So this mirror, you can see, get it at a right angle. You can see three of the coins. Let me see the camera. Let me see if I can get a good picture or view of it. So you can see the three coins, 1, 2, 3. There would be a fourth one if there wasn't this plastic piece right here. So I think that's why there's not a fourth one, but you can kind of adjust the angles and where it's at to get different variations of it. So you can kind of see that there's 2 in there, and then there's 1 over here, 1 over there. So that's actually 5 that you can see right there, changing the angle of it. So that one's pretty cool. And it said put it up to your face and wink. Oh snap! Okay, so on this mirror, you're probably not going to be able to see it because it's in my view. So on this side of the mirror, I can see my eye wink. On this side, I can't. So my eye's winking on this side, but I'm winking on my right eye. So the left, it's pretty weird. So if I wink my right eye, the left side of the mirror shows my winking eye, and the right side shows my left eye. So that's pretty interesting. And I don't have a printed piece of paper, but I can kind of do it with this. So it's just kind of weird looking, trying to get that way it's looking. It's just, I think it's backwards. The everything's reversed. And that. Rotate a pair of mirrors and keep them at right angles to each other. Does your image rotate also? Then place the mirrors 60 degrees apart so that you can see your face. Again, rotate the mirrors and see if your image rotates. Amazing. I can't really separate these mirrors, can I? Oop. I didn't know. Keep them at right angles of each other. Does your image rotate also? So if you, it rotates across the mirrors, but doesn't rotate. Ow, that kind of hurt my finger. I think I'm doing it wrong. 60 degrees? I don't have a protractor, so I don't know what 60 degrees is. I don't know if I'm doing that right. I don't know how you were supposed to rotate it. It didn't have any directions on that. But it does kind of rotate, but like my face doesn't rotate. Here's a pinhole camera. Make a pinhole camera as illustrated below. Cut one end of a small cardboard box and cover the end with tissue paper or wax paper. I decided to go with wax paper. Make a clean cut pinhole at the other end and aim the camera at a bright object in the darkened room. And you see an upside down image of the tissue paper. Then photographic film in vogue. Students replace the tissue paper with an unexposed photographic film, which we can't do. Covering the back so that it was light tight and covering the pinhole with a removable flap. All ready to take a picture, exposure times differ depending principally on the type of film and the amount of light. Lenses on today's commercial cameras are much bigger than pinholes and therefore emit more light in less time. Hence the term snapshot. For now, it will be enough to view images on the tissue or wax paper. So I am going to use a lighter instead of a candle because that's what they were using in the book to kind of just look through. And the wax paper is actually kind of blurry, so it's like you can barely see through it, but you can kind of see how it kind of looks upside down through it. I don't know if the pinhole, you're going to be able to see through the pinhole. Can you see through there?
A little bit.
Okay.
Well, I can see the light flashing on this side.
Yeah, it's just trying to get it like close, like all in it. How about that?
Hold on. Oh, it's just sitting there. Oh god, can't find the camera.
That's all right.
All right.
It kind of works. Okay. And then, why are skies blue? Why do the sun sets/rises? Why are they red? Explain your knowings and add to your appreciation of nature. Blue light is scattered in all directions by tiny molecules of air in Earth's atmosphere. Blue is scattered more than other colors because it travels in shorter, smaller waves, making the sky most of the time blue. Because the sun is low at the horizon, sunlight passes through more air, and the sunset or sun rises than during the day. When the sun is higher in the sky, more atmosphere means more molecules to scatter away the violet and blue light away from your eyes. This is why sunsets or rises are often yellow, orange, and red. So it's less molecules that it has to go through as it peaks the horizon, but as it's up top, it actually has more molecules to come through, making the light less of a color affected. So that's why the sunrise and sunsets are red and the sky is blue. For understanding of appreciation of nature, you kind of get an understanding of how it works, why it happens, and what colors we see. As an artist, you can really appreciate the way that the light goes through molecules and how you see it, and your eyes and your retinas perceive light as colors. And that's how I kind of appreciate nature for what it is. That's it. Thank you.